So we have here this pair of friction problems, which look like identical, but they're quite different in terms of the type of friction and what it means and how we approach the problem. Overall, we'll still sort of use similar techniques, but it's really the interpretation that's going to be significantly different between the two. So let's first read it and try and decipher the picture. A 10 kilogram block is on a surface with mu s equaling 0.35. Mu s is the coefficient of static friction and it is unitless between block and surface. A 50 Newton force pulls on the block. Does the block move or stay still due to the static friction? So, kind of based on the wording, you can see that the static friction is really about a force to overcome uh, the way that static friction works is it sort of fights back whenever you pull on something, but if your force is larger than the static friction can provide, then the block starts moving. Otherwise, the block just doesn't move at all. And so let's think of this from a few perspectives. Well, first let's talk about the equation. Fs, the coefficient of static friction, is, well, mu s times n, the normal force, but it's going to be not an inequality. It's going to be less than or equal to mu s n. So, well, actually, let's first draw the force diagram to really discuss what this less than or equal to means. But essentially, the static friction force is a force that can change. And so surely we have this 50 Newton force. I'll call it Fp. It's going to be equal to 50 newtons. We won't worry too much about positive or negative. That will come when we first consider this coordinate axes. We get to decide what direction x and y is. But when we start mixing it into the equation, into equations, then we worry about positives and negatives. So what other forces are acting on this block? Well, if we can see, if we draw a little circle around it, you can see, yes, it's touching that 50 Newton force, but it's also touching the floor down here. And so we got to consider the force from the floor. We got to consider any long-range forces, and there are actually two forces that the force is providing. One of them is a normal force. There's a long-range force due to gravity, and the other force is friction. Okay, and so this downwards force due to gravity, and we're going to pretend that that's perfectly straight down. But yeah, that we have this downward force, which is going to be equal to the mass times gravity, mg. And there's a normal force, which we don't immediately know. It's not immediately obvious exactly what this force is. One more force here is the friction force, which is going to fight the motion that we want to pull this at, but we're not going to be able to necessarily know whether we beat that motion or not. One possibility is that we have a short static friction vector like this, and so this is our Fs vector. And in this case, you can see that the net force is going to be a little bit to the right. This is F net, the sum of the vector sum of all forces. In this case, static friction loses and the pulling force wins, and we have a net rightwards acceleration. It could be the case that the arrow equals. Static friction is strong enough to equal the pulling force, Fs, and in which case the net force is 0. There is no net force, and there's no motion. If we started with a block that wasn't moving, then there's no motion. And so this is what we need to find out is this friction force going to be able to overcome, or is it going to be able to match that 50 Newton force, or is it going to be too weak? Okay, and so the way to find out is we got to find out what this mu s n is and see if that is bigger than or equal to 50. And if it is, then our static friction force is going to be equal to 50. It's going to match that 50 Newton force. It wouldn't make sense if that force is 50. It wouldn't make sense for the static friction force to be larger, like let's say 60 newtons, because what would that mean? That would mean we would have a negative net force, and for some reason that means that you pull to the right, and for some reason the block moves to the left. That's not really sensical, and so that's why we have this less than or equal to idea, and yeah, we don't always compute exactly what mu s n, like that's not always going to be the force that's provided by static friction. It's just the maximum force that static friction can output. Okay, so let's get rid of some of this nonsense here. Don't need these, don't need this. Oh, we don't know how long. Let's keep it at some vague leftwards vector. We don't know if it's long enough or not. Okay, so how do we make any progress here? Well, if we've got a force diagram, very likely we're going to use the most important equation in the class, F net equals, well, another way to put it is the sum of all forces, which is equal to mass times acceleration. This is Newton's second law. Okay, and so how is this going to help us? Well, we know some information about the motion of the block, or we want to know some information about the motion of the block, and we know slash want to know about the forces on the blocks. Okay, so we want to connect these two ideas, and so that's what Newton's second law does, is it connects forces to motion. And so if we look at the diagram, and I think you can intuit this, what we'll see is that, well, the normal force needs to be balancing gravity. How do we know that? Well, the way that we know that, and first actually let me be clear about what F net is. F net is equal to, it's a vector, so it's got an x component and a y component. Oops, so I don't need this vector now that I'm splitting it up into component forms. I hat plus F net y j hat. We can split it up into its components, and we can see, let's take a look at this F net y for a second. F net y is equal to the sum of all y forces, of all the y forces. It's going to be m times ay, the y acceleration. The block is on the table. It doesn't matter how heavy it is. It's not going to accelerate up or down. It's only going to accelerate potentially to the right or potentially not at all, but it's not going to accelerate vertically. And so AY is therefore 0. Okay? AY is equal to 0. And so uh, how do we formally reach that this means that the normal force is equal to gravity? Well, we're going to do this sum by being careful. Now we're going to consider the directions. Look at the y direction. This y direction is up is positive, down is negative. Look at the upwards components of all vectors. FP and FS are all horizontal. They have no vertical components. That's good. That makes the math easier. N is all positive, and so n, the full n, we don't need to worry about cosines or sine or anything. N is positive, and Fg is all negative, so minus mg is equal to 0. This here is this sum. This sum is n minus mg. And we can just put mg on the other side, add it to both sides, and therefore equals m times g, which is 10 kilograms times 9.81 meters per second squared, or 98.1 newtons. Kilograms meter per second squared is a newton. We did that formally, so we used Newton's second law to formally show that the normal force is equal to gravity. You don't have to do that. If this is an exam, or even if this is a homework problem, you don't have to go through all this trouble. You can intuit it by looking at the picture and looking at the diagram. You can kind of show, like, immediately see, yes, the normal force in this case has to equal gravity. It's not always going to be equal, but it is in this case. Good. This is going to help us because now we can compute this value. Mu s times n is 0.35 times 98.1 newtons. And again, the 35 value is unitless. Oh boy. Newtons. It's a unitless number. Mu is always a unitless number. And if you multiply those together, you get that this is equal to, and let's write this down here, 34.3 newtons. The maximum friction possible is 34.3 newtons, which is weaker than the rightwards pull of the 50 newtons. And actually, let's go ahead and we'll do this in another color. We'll do this over here. So we did the y. We can do the x as well. F net x is equal to, and if we sum all the x values, it's going to be 50 newtons, the FP, minus, since friction is leftwards, minus the 34.3 newtons. And we should be able to find that there is a net rightwards force of, it looks like 15.7 newtons positive, which means it's to the right. And so, yeah, the pulling force wins. And so the block will move. It's not clear. You can try and get to the acceleration, but it's not going to be clear because once it starts moving, it's no longer a case of static friction. Yeah, it's not going to necessarily have to do with this 34.3 newtons anymore. But we can beat 34.3 newtons. That means the block will move. Okay, now let's look at this scenario again, but now under a kinetic friction problem. So the same 10 kilogram block has a kinetic friction of mu k equals 0.22. After it is pulled with 50 newtons, what is the acceleration vector? Now, the kinetic friction is actually usually smaller than static friction. I wonder if it's strictly always smaller, but it definitely, at least most of the time, I can't think of a scenario where the static friction would be larger than the kinetic friction. Once an object is moving, it's sort of easier. It's hard to get it to start moving than it is to keep it moving in general. Now, we're going to solve this again slowly and formally. The last problem took us 12 minutes to get through. It doesn't have to take that long. I think you can jump to the answer very fast if you know what you're doing. But we are going to take it slow and once again do a force diagram. So it's the same one. We have this F pull is 50 newtons. We still have that the downwards pull due to gravity is mg downwards. We have n. We can use the same logic. We can use the same logic to say that actually n, it has the same magnitude as the gravity. And then we have the the kinetic friction, which necessarily must be smaller than the pulling force, or if it wasn't, then we would stop all the way down to 0. So what is the acceleration vector? Okay, so once again, the connection between our forces and acceleration or motion is Newton's second law, F net equals ma. So we want to figure out that acceleration vector. We're going to have to figure out both the x and y components. We've already done that F net y. It's going to be the same conclusion is mass times 0 because ay is actually 0. There's no way that the block is moving up or down, or else it would be flying in the air, or it would be digging its way into the table. It's not doing that, and so there's no y acceleration, and so the acceleration vector is only going to have an I hat and no j hat components. So that's cool. That's half our problem, isn't it? And so the rest of it is F net x. which is going to be equal to, well, the 50 Newton pulling force and the leftward pull of a friction, which this time Fk is going to be equal to mu k times the normal force. So minus minus, so this is Fp minus Fk. So this is going to be equal to 0.22 times the normal force, which is mg, which we had decided was 98.1 newtons. Okay, now if we go ahead and do this multiplication and this subtraction, we get that this is going to be 50 newtons minus 28.4, 21.5, sorry, 21.58 newtons. And if you do the subtraction, that's where we get the 28.42418 newtons is the net Fx. But Newton's second law says that this has to be equal to mass times acceleration in the x. And so, yeah, don't forget that our goal was to look at for the acceleration vector, which means that I'm looking for something that looks like this. A vector equals, I don't know, something ax I hat plus ay j hat. We already decided that ay is 0. Now we're finishing up ax now. So we know the mass. We know that the mass is 10 kilograms, and so therefore we just divide both sides by 10 kilograms, and we get that ax. So let me just make sure that's clear. Divide by 10 kilograms, since that is the mass. Divide by 10 kilograms. We get that ax is equal to 2.84 meters per second squared. Maybe it's just 2.8 if you want to consider significant figures. 2.84 meters per second squared. And so the final answer is that the A vector is equal to 2.84 meters per second squared, or just 2.8 I hat with no j hat component whatsoever. Okay. And so I think kinetic friction is a little bit easier than static friction. You don't have to worry about the inequality. You just a little bit more plug and chug. But the scenarios can get complicated in computing what this normal force is. When it's directly up and down, when the surface is horizontal, then usually it's simple. It's just equal to gravity, unless for whatever reason you have another force pulling down on this block. In which case the normal force would increase. But we'll save that for another time. Hopefully these made sense and this clears up any differences between static and kinetic friction.